Ah, pizza. There's nothing quite like it. The aroma, the toppings, the algebraic possibilities.
Care to run that by me again?
Think about it. When you order a pizza, you know how much it costs by the size of the pie. And you know how much each additional topping will cost you.
So you can calculate your cost for a slice or for any size pie with 1 topping, 2 toppings, or 10 toppings.
And before you know it, you're engaging in some algebraic thinking. Algebra helps organize patterns to represent lots of situations in the real world.
But in order to work effectively with algebra, you need to be familiar with the language of algebra.
So that you can translate everyday expressions into algebraic ones.
Just like there are relationships between people, there are relationships between numbers. Take that father and son over there.
Right. In addition to their parent-child relationship, there's a relationship between their ages that we can explore.
No matter how old he gets, that boy will always be younger than his dad. That's a relationship in age and in number, right there.
Let's play around with this a bit. Say we know that Dad is 30 years older than his son.
So if Dad is 31, his son would be 1. Now maybe Dad is 39, then Junior's 9, and looking ahead when Dad's 48, his son will be 18.
This pattern holds true for any age. No matter how old the father and his son are, they will always be 30 years apart in age. If you know how old one is, you can figure out the age of the other.
To show this algebraically, the first thing we need to do is assign a letter to represent Dad's age.
So why, you might ask, would we use a letter as a number? It's simple. In algebra, we're often looking for a way to generalize or find a rule to help explain a relationship that will hold for any situation. Here, Dad is always 30 years older than his son.
This isn't just true now. It was true before, and it will be true in the future. We're not thinking about just one number, just one case. We're thinking about many cases with numbers that may change. We use letters to describe these kinds of numbers, and we call them variables.
A variable represents a number or a set of numbers that can change. Here, that is Dad's age, or n.
Then we can describe Junior's age as n minus 30, since we know that Junior will always be 30 years younger than Dad. The 30 is a constant. A constant is a known quantity that stays the same.
Now we have an algebraic expression that describes this relationship. An algebraic expression is a mathematical phrase that contains variables, constants, and symbols for the operations performed on them.
Operations like adding, subtracting, multiplying, dividing, raising to a power, taking a square root, and so on.
An algebraic expression can be made up of many different quantities added together or subtracted from each other. These quantities are called terms. A term may be a variable or constant standing alone, or it may be a product of different factors.
Writing algebraic expressions is a way of describing relationships between numbers or sets of numbers. It's like writing a rule for something that holds in many situations. Let's see. I think I'll get pepperoni.
Plain sounds good to me.
Did you know that on any given day, the owner of this restaurant sells twice as many plain pizzas as ones with toppings?
Really? I'll bet we can write an algebraic expression to show the number of plain pizzas he sells based on the number of pizzas with toppings sold. For instance, if he sold 1 pizza with toppings, then he would have sold 2 plain pizzas. If he sold 2 pizzas with toppings, then he would have sold 4 plain, 3 with toppings, 6 plain, and so on. And this relationship holds no matter how many pizzas are sold. There are always twice as many plain pizzas sold as ones with toppings.
What if the owner sells 1,000 pizzas with toppings in 2 weeks? The same rule applies, and you can safely project that he will sell 2,000 plain pizzas in that same time frame.
We can write an algebraic expression to describe this rule or pattern. If we define the variable x as the number of pizzas with toppings sold, then we can express the number of plain pizzas sold as 2 multiplied by x, or 2x. The 2 is called a coefficient, a numerical factor multiplied by a variable or variables in an algebraic expression. In algebra, we show multiplication by using parentheses, or a middle dot, or even just by writing the factors right next to each other.
And you can choose anything you want to be the variable, as long as you clearly define what the variable represents. Most often, letters are used for variables. What's important to understand is that a variable represents a number or set of numbers, not a thing. In this case, x represents the number of pizzas with toppings, not the actual pizzas themselves.
That's a common mistake, using variables as labels. For example, if we wanted to write an expression to represent the total number of slices in any given number of pizzas, P equals 8S seems like it would work, right? I mean, P for pizzas and S for slices seems like it would make sense.
But not so fast. Let's say we have 5 pizzas. Then there'd be a 5 on the left side of the equals sign for P. That would mean that 8S equals 5. If we solve for S, we get S equals 5/8.
That would mean for 5 pizzas, there would be a total of 5/8 of a slice? I don't think so.
This doesn't make sense because we've used our variables as labels. By using P for pizza and S for slice, the letters aren't representing numbers. So we can't write an expression that shows the relationship between the number of pizzas and the total number of slices.
Okay, let's look at this another way. For 1 pizza, there are 8 slices. For 2 pizzas, there are 16 slices. For 3 pizzas, there are 24 slices, and so on. Now, it's easy to see what's going on here. If we let the variable x represent any number of pizzas, then we can always multiply that by 8 to calculate the number of slices. 8x is the expression for the total number of slices.
If we made 5 pizzas, then x would be 5, and we would have 8 times 5 slices, or 40 slices altogether. Now this is an expression that makes sense, and it confirms what we know should be true.
That the total number of slices should be greater than the number of pizzas. The owner of a concession stand notices that for every bottle of soda sold, 4 bottles of water and 2 bottles of fruit juice are sold. Which of the following expressions represents the total number of bottles the owner should stock? Let X represent the number of soda bottles sold.
To find out
should stock. Let X represent the number of soda bottles sold.
To find our answer, we can start by looking for the choices we can eliminate easily. Right away, we can see that choice A is out because it's an equation. Our question is asking for an expression representing the total number of bottles the owner should stock. And algebraic expressions don't have equal signs.
And we know it's not D either. Why? The letters in this expression are being used as labels, not variables. We want to write the number of water bottles and fruit juice bottles in terms of the variable X, the number of soda bottles, because we know how the numbers are related. For example, there are 4 times as many water bottles as soda bottles, so an expression for the number of water bottles in terms of soda bottles would be 4X. 4W sounds like we're multiplying 4 by the number of water bottles, which is incorrect.
Choice B looks better. The expression 4x does represent the number of water bottles in terms of the number of soda bottles. But the 2 as a constant is a problem. It implies that the stand will always stock exactly 2 bottles of fruit juice, which would be gone before breakfast was over.
So the correct answer is C. The 2x represents the number of bottles of fruit juice sold, which is twice the number of soda bottles sold. The 4x is the number of water bottles sold, and the x is the number of soda bottles sold.
Put these together and you know how many bottles the concession owner needs to stock.